Okay, so for your quiz on Thursday, you need to know how to do the mass spectrometer. And so we have here a mass spectrometer design has the following components. Positive ions of charge Q and mass M are formed at source S and accelerated through a potential difference V sub G. The ions pass through the grid and into a velocity selector where there exists a magnetic field B, as shown in the figure, and an electric field. When the charges leave the selector, they enter a region where the same magnetic field is present, but there is no electric field. Respond to the following in terms of Q, M, V, G, and B. So all our answers have to be in terms of Q, M, V sub G, and B. So question A asks us determine the speed V0 of the charges as they pass through the grid if they were initially at rest as they left the source. So what we're assuming here is that the source, V equals 0, and then they're going to gain some speed due to that potential. Now, what we have to do is find out what is the speed V0 at that point. So in this case, the velocity is being caused by the potential. So we have to relate the potential difference somehow to the speed. Well, what we do know is that once it's moving, it's going to have kinetic energy. So the final kinetic energy is going to be 1/2 mv0 squared. Initially, it has potential energy, and that potential energy is given by Q Vg. So the initial potential energy at the source is going to have to equal the final kinetic energy after it's passed through the potential V sub G. So all we have to do is set these equal to each other and solve for V sub 0. So we can multiply both sides by 2. And then divide both sides by m. And finally, take the square root. And that would give us its initial velocity at this point right here. So it's been accelerated by the electric potential to a quantity 2q Vg over m. Part B asks us, sketch the path of the charges after they leave the selector. So remember that at the selector, and if we read carefully, it says the ions pass through a grid and into a velocity selector where there exists a magnetic field B as shown in the figure and an electric field. So when they're going through the selector, only the ones that were accelerated through here are going to pass through, but they're positive charges. So we have to ask ourselves, which way is a positive charge going to go after it's left the selector? So if I put my charge right here, and remember it's positive, which way is it going to go? By using the right-hand rule, I know that its initial velocity is up, the magnetic field is inward, so the force on the charge has to be to the left. Now, because it's a uniform magnetic field, it has to make a circle. So the trajectory of the charge is going to be a half circle. And so that is the trajectory it would follow after it's gone through the selector. Part C says determine the radius of the path. So it's asking for R. Well, what's causing the centripetal motion? We know that it has a magnetic force on it, so we're looking for this R right here. So I know that the magnetic force has to equal the centripetal force. This is QVB. I don't need the sine theta because the velocity and the magnetic field are at right angles to each other. You can see right away that I can cancel out a V from both sides. And now I can solve for R, which is mv over qb. However, that is not one of our fundamental quantities. So we take our answer from A, which is the velocity it would have after it's going through the selector, and put that in there. So R becomes m square root of 2q vg over m divided by qb. And if I wanted to clean it up a little bit, I could just as well plug in the m in the square root sign. So finally I have R is equal to square root of 2q m squared vg divided by m q squared b squared. I can cancel out some of the components. So at the top, all I have left over is 2m v sub g divided by q b squared. For the last part, question D, I'm asked, charges leaving the source may have non-zero speeds. What electric field, magnitude, and direction must exist in the selector to ensure that only the charges with V sub naught leaving the grid will pass undeflected through the selector? What this means is that here at the selector, we have the magnetic force is pushing it left. So we have to have an electric force at this point right here that cancels out the magnetic force. So we can say that F of magnetism has to equal the force of the electric field. This is QVB, and then this is just QE. So we're solving for E, and we have E is just VB. But V is not a fundamental constant, so we have to substitute it with what we got before, which was the square root of 2qvg over m times b, or under all one radical, 2qvg b squared over m. And the electric field would have to be directed to the right.